Okay, so let us start the further analysis in differential mode and common mode. Now, what we have seen in the previous classes is the qualitative analysis in differential mode and in common mode. Now, what we are going to do is quantitative analysis. So, simply speaking, if I just write this in layman's language, we are going to see derivation for differential gain. I will call it as AD. Derivation for AD. So that's a different way of just saying that in the quantitative analysis, now we are trying to quantify with the help of some parameters what is this gain going to be. So to start with, this derivation is also asked for 10 marks in the exam, and it's better to write down the way I am writing. So first we will start with the basic differential pair circuit diagram. This is the basic differential pair, and let us write here the two outputs, that is V01 and V02. Here I will write it as RD and RD only, that is RD1 is equal to RD2, and finally here we have a current source which is going to be ISS. So let's call this as transistor M1. This is M1 and this is M2, and let us also mark for our convenience the drain and source. So this is drain, this is source, this is drain, and this is source. Now what we are trying to do is the differential mode analysis. So we will require two signals, V in 1, and on the other side we will also require V in 2, and this at the top would be VDD. So simply speaking, we will have this particular diagram. Now in the second step, what we are going to do is we will just take this thing. So we all know what is superposition theorem. So superposition theorem means if there are two voltage sources in the circuit and if you want to see the effect of both of them, then what you can do is you can give the inputs one at a time and then finally add the responses. So we are going to see something similar. So first we will see effect of V in 1 on V01 and V02, and then we will see effect of V in 2 on V01 and V02, and then we will add the responses. So when we say that we want to see effect of V in 1, so what we will do is we will make V into equal to 0. We will make V into equal to 0. So I'll just connect this to ground and say here V into is equal to 0. So please write this. V into is equal to 0, and the current source also has to become equal to 0. The current source has to be equal to now 0. So as we all know current source equal to 0 means open circuit and voltage source equal to 0 means short circuit. So please copy these two diagrams first, then we will move to the next diagram. Once you are done with this, just write done in the chat box. So to analyze this circuit, we are actually using superposition theorem. And in this is the first case, effect of V in 1 on V01 and V02. Once you are done copying this, please write done in the chat box. So like I said again, that quantitative analysis means we are trying to quantify the things now. If we speak about gain, we should speak in terms of some parameters or a formula. So basically quantitative analysis in differential mode is derivation for AD, and quantitative analysis in common mode would be derivation for AC, that is common mode gain. And in the exam, if they ask you derive the equation for AD and EC, then it is nothing but quantitative analysis in differential and common mode together. Yes, once you are done, please write done in the chat box. Yes. Okay, so let's go a bit ahead. So now what I am doing is, since this ISS is 0, I am just drawing one more circuit here, and so let's take this circuit itself. And let's go down, paste it here. So some small changes here would be, this is going to be VDD itself. This will be connected to ground only, and here this current source, now we will show it as open circuit. We'll show this as open circuit. So that's the way to show ISS is equal to 0. This is the way to show ISS is equal to 0. And if we see furthermore, we can do like this, that is, this M2 I can replace it by its AC equivalent. So see here, what am I doing? Just for analysis sake, this RD is as it is. So I am replacing it by the T model of the MOSFET. T model. So this I am keeping it as it is, and this value, as we know, this will be 1 by GM2, and this value will be GM2 into VGS2. And Vn2 will be equal to 0. So there is no doubt in that Vn2 will be equal to 0. Now just for the sake of it, I am just again identifying, this is still my source, this side is still the drain, and this side is still the gate, and the current flowing in this direction I is equal to 0, and this is what we generally call it as node X. That's what we generally call it as node X. And also ISS is equal to 0. ISS is equal to 0 means here will show it as a open circuit. So if you open the book, certain things are given very directly and these intermediate steps are skipped. So it's sometimes difficult to understand directly from the book, and that is why I am just solving this for you so that you can understand. So now I want you to draw this circuit and this circuit. And you can see now that if we start from here, this is VDD, then we have RD, then we have drain source, then we have M1, that is the source of M1. Source of M1 is now connected to source of M2. Then we have a resistance 1 by GM2, and this point X is as good as at zero potential. Is as good as at zero potential. So V in 1 can actually not see anything beyond this point. So beyond X it cannot see because it gets a ground at point X only. So this part of the circuit, that is RD, V02, GM2, VGS2, they constitute one part of the circuit which is connected between VDD and ground, and this 1 by GM2 along with M1 and RD constitute another part of the circuit which is again connected between VDD and ground. So actually this circuit becomes somewhat like this. Are you done copying this circuit? You can also draw this directly if you want, the second one. So actually now what we get is something like this. We have VDD, then we have RD, then we have M1, This is connected to V in 1, and here we have 1 by GM2. This is nothing but RD, and here we have V01. So we have V in 1 and we have V01, and on the other side of GM2 there is point X, which is as good as connected to ground. So I am taking the help of the T model of the MOSFET to understand this concept: drain, source and gate. Now if we want to analyze this circuit, okay, again we can take, so this circuit now becomes this way. See here how I am drawing it. This is current. This is my transistor M1, 1 by GM1. Here we have the node X of M1, and here we are connecting our input, that is going to be V in 1, and here this is going to be GM1 VGS1. So this is basically the drain, source and gate of the transistor. So AC wise, VDD is connected to ground. So this RD is connected between drain and ground. So this is RD is connected between drain and ground, and here we have V01, and at the source we have another resistance, that is 1 by GM2. Now common sense should tell you that V01 is going to be minus GM1 VGS1 into RD, because the current will flow like this. That is why the minus sign from ground to the output. And here V in 1 is basically voltage drops across these two. So here this is VGS1. So what will be the voltage drop between point X and ground? So V in 1 is going to be the current, that is GM1 VGS1 into the resistance 1 by GM1 plus 1 by GM2, and V01 upon V in 1 is equal to, if we divide this GM1 and VGS1 will go away, and what we will get here is minus, very important, RD upon 1 by GM1 plus 1 by GM2. 1 by GM1 plus 1 by GM2. So GM1 and GM2 can be different also, and they can be same also. So we can write here V01 is equal to minus RD upon 1 by GM1 plus 1 by GM2 into V in 1 into V in 1, that is output in terms of input. But now we have calculated only V01, but even V02 is there. Even V02 is present. So we have to analyze V02 also. So first you draw this much, then we will go ahead. So we will take this as equation 1 rather than the above one. So you can see that T model is much better as compared to pi model when it comes to the analysis of differential modes. Yes, any doubts in this? Please unmute and ask. Please unmute and ask. I will wait here till you copy this. Now this is very difficult to see. This circuit is very difficult to see. Otherwise, when we are applying the superposition theorem. So what we are actually trying to do is, we are trying to see what is V01 minus V02 due to V in 1, and we are again trying to see what is V01 minus V02 due to V in 2. And once we know both the responses, we will add those responses and then comment on what is the differential gain. So that is the strategy. Yes. Please write done in the chat box once you are done drawing this. And in the meantime, those who are finished can think about how to now calculate V02 in terms of V in 1. So if you see here, first I saw V01 in terms of V in 1. Now V02 also is very much present. So we want V02 in terms of V in 1. So how to do that? So anyways, we will start with V02 and then move forward. Okay. Have you completed this? I think I have given enough time. Anyway, so I'll just go ahead with the calculation of now. What you can see on screen is V01 in terms of V in 1. Now I am going to calculate V02 in terms of V in 1. So let's write similarly. Calculate V02 in terms of V in 1. So for this, the circuit would be, now I will start from the M2 side. So first I am drawing transistor M2. So here I will write GM2 VGS2. Then I have my 1 by GM2, sorry, and this is node X, and as you all know that this point is connected, the gate of M2 is connected to ground. The gate of M2 is connected to ground. So this is the drain of M2, and you can see between the drain of M2 and VDD, which is AC wise ground, there is RD. So I am writing here RD, and here we have V02. This is basically the source of M2, and the source of M2 is connected to the source of M1, is connected to the source of M1, and the first in line there is going to be here we will have 1 by GM1, and M1 now we can show it reverse because we are coming from M2 to M1. Okay, and then here at the drain of M1 we have RD, and the other side of RD is connected to ground. So I am just marking this. This is source. This is also the source of M1. This is the gate. This is GM1 VGS1, and here what is connected is our V in 1, and this point is the drain of M1. So here I would say this is M1, this is M1 MOSFET, and this much is M2 MOSFET, M1 and M2 MOSFET. Now we have to apply few logics. So one we can apply very quickly, that is V02 is equal to, we can directly write minus GM2 VGS2 into RD. That is the first thing. Now we have to write V in 1. Now we have to write V in 1. So either you can write V in 1 in terms of VGS1, GM1 VGS1, or you can write it in terms of GM2 VGS2. So please copy this. Here I is equal to 0, and here also I is equal to 0. So if you see that, if you consider this as a node, then the incoming current should be equal to outgoing current. So you should note that the incoming currents are GM2 VGS2 and GM1 VGS1, and the outgoing current is 0. There is no outgoing current at all. So what we can observe here is GM2 VGS2 plus GM1 VGS1 is equal to 0. So obviously you can come to a conclusion that GM2 VGS2 is equal to minus of GM1 VGS2. That is by simple observation, or I would say KCL. And I keep on saying that electronics is all about KVL and KCL, nothing else. So with keeping this in mind, now you can see that V in is connected between this point and ground, and 1 by GM1 and 1 by GM2 are also connected between the same point and ground. So this node X here is connected to ground. And that is why we can say now that if you want to write it in terms of GM1 VGS1, then we can write V in 1 is equal to GM1 VGS1 into 1 by GM1 plus 1 by GM2, and GM1 VGS1 is nothing but minus of GM2 VGS2. So we can write therefore V in 1 is equal to minus of GM2 VGS2 into 1 by GM1 plus 1 by GM2. And if you look at these two equations, V in 1 and V in 2, let's call it as A and B. If you take A over B, what you will get is that minus signs will get cancelled, GM2 VGS2 will also get cancelled, and we would get V02 is equal to RD upon 1 by GM1 plus 1 by GM2, this entire thing into V in 1 into V in 1. So this is my equation 2, and the further this was equation 1. Now if we do 1 minus 2 subtract 1 or 2 from 1, we will get V01 minus V02 will be equal to 2 times of minus of 2 times of RD upon 1 by GM1 plus 1 by GM2 into V in 1 into V in 1. So now what did we actually calculate by doing such a thing? We calculated V01 minus V02 due to V in 1. So if I want to look at this expression in layman's language, this is V01 minus V02 due to V in 1. Why only V in 1? Because V in 2 you only made it 0, right? V in 2 you only made it 0. So everything would come in terms of V in 1 only. Now I want you all to repeat all this and tell me what is the value of V01 minus V02 due to V into due to V into. I want you all to calculate that. So first you copy down this, then we will calculate due to V into. Once you have copied this and drawn this circuit, please write done in the chat box. Here I made a small mistake. The upper one is M2 and this is M1. Other things are just So if you look at this closely, this ground and this ground, this is actually VDD grounded. This is VDD grounded. This is V in 1 is connected to the gate, and V in 2 is connected to the gate of M2, but V in 2 is equal to C. Yes. Please write done in the chat box once you are done with this. Any doubts? Unmute and ask. Unmute and ask. Okay, Hemant, still I will give 2 minutes for all of you to write, and in case of doubts, please unmute and ask. All I am doing is sticking to KVL and KCL. So now let's look at effect of V into effect of V into effect of V into. So what I'll do here is, now we start off with the same circuit, and here instead of V into is equal to 0, now we will make V in 1 equal to 0. Effect of, I will say now, we want to see V into. So we will keep this V into yeah. Can somebody quickly confirm whether you can see my screen and hear my voice?
Yes, sir.
Yes, sir. Okay. We lost the network for 1 minute.
Sir.
So here the changes have to get reflected. Now again here I'll see what I'm doing. Not pretty much the same thing. V into is no longer 0. So here we have, this is connected to ground now. V in 1 is 0. And here we have V in 2. So similar changes I will do in this. Just see what I'm doing. So what will change? Only the signets, only the signs will change. So let's make this V in 1 is 0. And here we have now V in 2. So what I'll do is, just for the sake of our convenience, I'll just flip this circuit and I'll call this side now as and do the changes to avoid some confusion. Okay. So here I will show the T model. This is 1 by GM1. This is connected to ground. This current I is 0. V in 1 is now equal to 0. And here you have M2 V into, and this is basically your M1 and M2. So this circuit slightly changes to, instead of V01, here I'll write now V02. Here V in 1 becomes V in 2, and 1 by GM2 becomes 1 by GM1. That's the small change. Again here also, instead of V in 1, we will have V in 2. This will be GM2, VGS2, and this will be 2. And the lower one would be 1. So here we would get, first we would get here now V02 is equal to GM2 VGS2 RD, and here V in 2 is GM2 again VGS2, and here we will now get V02 first in terms of V in 1, V in 2, and here we have V02 and V in 2. So that is my first equation here now, and similarly we will have here now V01 instead of 2 in terms of V in 2. So here this would be now a little bit different. This 1 and 2 need to be interchanged. So here we have V01, here this will be GM1, VGS1, 1, this will be 2, 2, 2, and M1 instead of M2, here we will have M1, and here we will have M2. So that gives me a small variation in the circuit as well. So this will be V in 1, V01, GM1, VGS1. This can still exist. This equation is still true, and here we have V into, that will be again GM2, VGS2 into 1 by GM1 plus GM2, and that I can write it as minus of GM1 VGS1, and because of this now we can write V01 is equal to this, and V01 minus V02 this time would be, instead of minus, there would be a plus sign. There would be a plus sign. So we actually got two equations. From these two analyses. So we use superposition theorem, and what we did is we calculated V01 minus V02 due to V in 1, and we want to now calculate V01 minus V02 due to V in 2. So if you look at this thing, first we have V01 minus V02 is equal to minus 2 RD upon 1 by GM1 plus 1 by GM2. This entire thing into V in 1. This is equation number 1. And when in the second case of superposition, we got V01 minus V02 is equal to plus 2 RD upon 1 by GM1 plus 1 by GM2, but this time it's going to be V into. Now when it comes to superposition, we always add the response. So I will say by superposition theorem, adding 1 and 2. So if we add 1 and 2, what we are going to get here? So we will get twice of so we should get here like this here. It's a very interesting thing. Twice of V01 minus V02 is equal to, here we have V in 1 and V in 2, so that will be minus 2 RD upon 1 by GM1 plus 1 by GM2 into V in 1 minus V in 2 into V in 1 minus V in 2. So this 2 cancels out, and what we are left with is V01 minus V02 upon V in 1 minus V in 2 is minus of RD upon 1 over GM1 plus 1 over GM2. 1 over GM1 plus 1 over GM2. So this is what we are left with. Yes. So I would write it in this way. Let's be very specific. This is V01 minus V02 due to V in 1. This is V01 minus V due to V in 2. So no need to have this 2 here. We can say because of both, V01 minus V in 2 will be now simply this, and there will be this 2 here. So we are adding 1 and 2 means not physically, we are only adding the V in 1 and V in 2. So let's say that, I'll give an example here. Let's say I want to calculate I in a branch. For that I am calculating I dash, then I am calculating I2 dash plus I3 dash. So in case 1 I get I is equal to I dash. In case 2 I get I is equal to I2 dash. In case 3 I'll get I is equal to I3 dash, something like this. Now when I want a combined I, when I want this I don't write 3I is equal to I1 plus I2 plus I3. I don't write that. What do? I simply say I is equal to, in one case I got this, in one case I got this, in one case I got this. So simply add this side. That is going to be my total I. So similarly here also, in case 1 I got V01 minus V02 as this. In case 2 I got this, and now I am only adding the two responses. So V01 minus V02 is this. And in this case what will happen is, this is nothing but change in output upon change in input, and that is minus 2 RD upon 1 by GM1 plus 1 by GM2, and this differential output upon differential input is basically your differential gain, that is 1 by GM1 plus 1 by GM2. Now here there could be a condition, if GM1 is equal to GM2, and that is likely to happen if W by L of 1 is equal to W by L of 2, then AD is equal to minus 2 times of RD upon 1 by GM1 plus 1 by GM1, that would be minus 2 RD upon 2 by GM1. So this 2 gets cancelled, and we will get AD is equal to minus GM1 RD, or you can write minus GM2 RD. And this is if GM1 equal to GM2. So you can see that the differential gain, what is your observation? The differential gain is the same as the gain of a common source stage. The differential gain is the same as the gain of a common source stage. However, here what you get is noise cancellation. However, what here you are going to get is noise cancellation. So that is why we say that differential amplifier is a better amplifier as compared to your single stage or common source kind of amplifiers. So if you want to copy this thing from the circuit, effect of V in 2 on V01. So I'll give you some time here. Please copy this. In the exam, if you don't have time to write so much, you can just write similarly V01 minus V02 due to V in 2 is the equation. If you have got minus, you will write plus. That's it. Yes, if there are doubts, please unmute and ask. So this is the first part. So after this circuit, you can directly go for this one. You can skip some steps and then go to this, get V02 first. So in the first case, you get V01 first, and in the second case, you get V02 first. But we are always seeing V01 minus V02, and that is why you get that slight change in the sign. So that's the reason. So just keep that much in mind. I think that would be good. So this is the circuit. Then we do a AC analysis on M2 side. Then we do an AC analysis on M1 side. When you do it on M2 side, you get V02. When you do it on M1 side, you get V01. And then you take V01 minus V02. And by superposition, you do this. So here I'll just add one small note. This is V01 minus V02 due to V in 1. This is due to V in 2, and this is due to both V in 1 and V in 2. Both V in 1 and V in 2. Okay, so it's 11 o'clock. Time for our first break of 15 minutes. So we'll just take a break and come back at 11:15. In the meantime, if there are any doubts, I'm here. So this problem that we are going to do is a very famous problem in the exam. So let's start with that problem. So the problem is something like this, that in the circuit given below, so this is the problem. Let me write it down first. Here we have again a differential amplifier. And this is RD, this is also RD, this is my M1, this is M2, and here we have V in 1 and here we have V in 2. So here what is given to us is this is M1, this is M2, and here we have our normal one, that is V01 and V02 with VD. So here the W by L of this transistor, let's keep it as W by L1 and this is W by L2. So what is given in the problem is that M2, so the first point that is given is M2 is twice as wide as M1. M2 is twice as wide as M1. So calculate AD if the bias values of V in 1 and V in 2 are equal. Of V in 1 and V in 2 are equal. So what is the objective here? So we have to calculate the voltage gain. So please copy down this, then we will write the solution to this problem. So what is given here in the problem is that M2 is twice as wide as M1. M2 is twice as wide as M1. That is W by L1. If this is W by L, then W by L2 will be twice as wide. Means what? It will have a width double that of M1. So W by L1 is W by L, then W by L2 will be twice of W by L. So please write it like this. Once you have copied the problem, write done in the chat box, then we will go ahead with the solution. So now what is given in the problem? Again, V in 1 and V in 2 are equal, so we can say that this point is common. So here VGS1 is equal to VG1 minus VS1, which will be V in 1 minus VP, and VGS2 is equal to VG2 minus VS2, which will be V into minus V. But V in 1 is equal to V in 2. That is why VGS1 is equal to VGS2. Hence VGS1 is equal to VGS2. Now if you look at the current equation, that is ID1 in the saturation would be mu n COX W by L1 by 2 into VGS1 minus VTH the whole square, and ID2 would be mu n COX W by L2 upon 2 VGS2 minus VTH the whole square. So here, where is ID1 and ID2? ID1 is flowing like this and ID2 is flowing this way. So if you see VGS1 is equal to VGS2, so these two terms will cancel out. This will also cancel out. Mu n COX by 2, mu n COX by 2 will also cancel. And what we will get here is ID1 upon ID2 is equal to W by L1 upon W by L, which will be equal to W by L upon twice of W by L. So which is equal to 1 by 2. So we can say ID1 is equal to half of ID2, or alternatively we can say ID2 is twice of ID1. ID2 is twice of ID1. Okay. We also know one more thing, that is ISS is equal to ID1 plus ID2, and ID2 is twice of ID1, so we can write here ID1 plus twice of ID1, so that is 3 times of ID1. So we can write ID1 is equal to ISS by 3. ID1 is equal to ISS by 3. And if we put this back inside this equation, we would get ID2 is equal to 2 ISS by 3. That is 2 by 3 times of ISS. And if you sum ID1 and ID2, you can see again they are equal to ISS. So this is the simple equation. Now we know AD, that is the differential gain, is minus 2 times of RD upon 1 by GM1 plus 1 by GM2. So if we are able to calculate GM1 and GM2, we should be able to calculate the value of AD. Now GM1 is equal to root of 2 mu n COX W by L ID1. But what is ID1? ISS by 3. So we can write GM1 is equal to 2 by 3, that is here 2 mu n COX W by L into ID1. ID1 is ISS by. Similarly, GM2 is equal to root of 2 mu n cox w by L, this time it will be w by L2 id2. Now w by L2 is how much? W by L2 is twice of w by L. So gm2 is equal to root of 2 mu n cox 2 w by L, and id2 is into 2 times of ISS by 3. So now we have to find out what is the values in terms of this. So let me just write this in a slightly different way. So we will write gm1 upon gm2 is equal to root of, this is 2 by 3 mu n cox w by L ISS, and gm2 would be root of 8 by 3 mu n cox w by L ISS. So this will give me root of 2 by 3 upon root of 8 by 3. So this will give me root of 1 by 4, and that will be 1 by 2. That means gm1 upon gm2 is equal to 1 by 2, and gm2 is equal to twice of gm1. Now we will use this formula and write the value of AD. Write the value of AD. So either you can write AD in terms of gm1 or you can write it in terms of gm2. It's up to you. So AD is equal to minus 2 times of RD upon 1 by gm1 plus 1 upon gm2 is now 2 times of gm1. So that will be minus 2 RD upon 2 plus 1 upon twice of gm1, that will be minus 2 by 3 times of gm1 into RD. So this is the value of AD. Now you can write this in terms of gm2 also. So AD is equal to minus 2 times of RD. So gm1 would be 1 upon gm2 by 2 plus 1 by gm2. So that would be this gm2 would go up. So calculate this. I made a small this thing. This is 4 by 3. Sorry, I forgot this 2. This is minus 4 by 3. Correct. And here this would be minus 2 RD upon 2 by gm2 plus 1 by GM2. So that will be minus 2 by 3 GM2R. So either you write it in terms of GM1 or you write it in terms of GM2. Yes. Now for your homework, you will try this. You will try this thing. Not, you will disregard this statement and you will do this. W by L1 is 3W by L and W by L2 is 2W by L. So you will solve for this as a part of homework. So this sum comes for 10 marks. So generally we should know how to deal with it. So what is the moral of the story here? That the differential gain increases if we change the W by L ratios of the transistor, but that will lead to different currents. ID1 and ID2 are now not the same, and that is the reason why your outputs might not be symmetric. So it's a matter of seeing the outputs in the lab. Though formula wise the gain says it is minus 4 by 3 GM1 RD, and so if you are done with this, please write done in the chat box. So first we establish the relationship between ID1 and ID2. Then we establish the relationship between ID1 and ISS and ID2 and ISS. And then we simply calculated GM1 and GM2. And then we wrote the formulas one over the other. And we established the relationship between GM1 and GM2. Then that gave us the liberty to write AD in terms of GM1 or GM2. In the exam, you can write any one. You don't have to solve for both. But you have to mention this relation between GM1 and GM2. So it is understood that the other thing will also come using this particular relation. Any doubts in this problem? Please unmute and ask. Are you done with this writing with this problem? Any doubts? Unmute and ask. And now let us go to the last part of this chapter, that is the quantitative analysis. In common mode. Quantitative analysis in common mode. So start drawing this. So here what we are now trying to do is, first thing, this is what common mode. This is common mode signal. So V in 1 is equal to V in 2, that is equal to VCM, or we can call it as V in CM, whatever you like it. Okay, let's use the book notation, V in CM. So here what we have to show is they both are the same, that is V in CM, and this is also V in CM, that is V in common mode level. Now, an important attribute of differential amplifiers is their ability to suppress the effect of common mode perturbations. That means if there is something common to both the sides, that automatically gets cancelled. Now, there is some limitation on this. That is, in reality, neither a circuit is fully symmetric nor does the current source exhibit an infinite output resistance. Neither a circuit is fully symmetric nor does the current source exhibit an infinite output resistance. That means M1 and M2 are having widths W by L1 and W by L2. Length somehow you can make it the same, but making widths perfectly the same is difficult. On top of it, there are resistances RD and RD. So we all know that resistances have some kind of tolerances, 5%, 2%, 1%, 0.5%, but they have some tolerance values and these values can fluctuate. You can also see I have written ISS, and ISS is actually implemented using a current source, and the current source will have a MOSFET connected in the place of ISS. Now, if we make the transistors really very small, then the R0 of the transistor which is used for implementing ISS is going to be large, it is going to be finite, it is not going to be infinite. And that is the reason why a small fraction of the input variations, can appear at the output, and that is the reason why we have to talk about the common mode response. The first notion of common mode response is that if everything is symmetric, then V01 will be equal to V02 and V01 minus V02 will be 0 and common mode gain would be 0 only. Okay, but that is our notion. But in reality, this condition can happen only if the circuit is fully symmetric or the current source exhibits infinite output resistance. So these two conditions are very difficult to happen simultaneously due to what? Due to technology constraints. Why technology constraints? Because if we try to make these MOSFETs smaller and smaller, we all know now that the channel length modulation parameter creeps in, and the effect of that on the current source is very high. And that is the reason why we have to deal or find out how much part is actually going to disturb the circuit. Therefore, we first assume that the circuit is symmetric, but the current source does not have an infinite impedance. So what we say is, somehow let me assume that RD is the same on both the sides, but the current source that I am using is not going to have infinite resistance. Current source must have, an ideal current source must have infinite impedance, but we have to deal with practical situation, and that is why we can somehow claim that I have maintained symmetry, but I cannot claim that I have made a ideal current source. And that is the reason why, since that ideal current source is not possible, what actually happens is somewhat like this. I am just taking this circuit. So here all this is fine, but actually this current source is implemented in this fashion. I have already shown you that, but still I'll repeat it. This is my VDD, and actually the current source is like this. So it is implemented through a current mirror. So we have already discussed about this, but still, since we are doing common mode response, let's keep that in mind. So the current flowing through this, let's say this is M3 and this is going to be ISS, and my claim is that you will never be able to make an ideal current source. And if it's not an ideal current source, then ideally the in the saturation region this M3 should be perfectly flat. But actually, since the channel length modulation comes up, there is some R0, there is some resistance, and this resistance is high in the saturation region, and that is the reason why we can model this entire circuit by a so instead of this ISS, initially I am writing here RSS. What is the value of this RSS? It is very high, okay, but so I will say here RSS is very high but not infinite, and since it is not infinite, there can be a problem. So please draw this circuit first, and then we will see the analysis of this circuit very quickly. draw this. Once you are done drawing this, please write done in the chat box. You have exactly 2 minutes to draw. Draw it quickly. Why this is high resistance? Because M3 would be in saturation, and in saturation the slope is very small. So slope is very small means resistance is very high. Now, one very important thing here again, you can see V in 1, V in 1 and V in 2 are equal. That is, we are applying V in Cm at both the terminals. So, if V in 1 and V in 2 are same, then we can claim that V01 and V02 are also same due to symmetry. So we can claim that V01 and V02 are also the same due to symmetry. So if V01 and V02 are at the same potential, then what we can do is we can do something like this. See here what I'm doing. I'm just removing this unnecessary namings. I'm shorting this. So since V in 1 and V in 2 are same, let us say that this is point X, this is point Y. So point X and Y will be at the same potential. Point X and Y will be at the same potential. So owing to symmetry, Vx remains equal to Vy. Hence, the two nodes can be shorted. Since M1 and M2 are now parallel, they both share their respective terminals. They both share their respective terminals. Now, what actually happens here is we are interested in analyzing this circuit now. So, we have, so I'll just copy this circuit only. No need to draw it again. I'm just copying this for our reference. So this same circuit, I can draw it in this fashion. That is, I start with from VDD. Now you can see this RD and this RD are in parallel to each other. So this is RD parallel with RD, that is going to be RD by 2. Then this is, I am showing a MOSFET here, but this is M1 in parallel with M2. M1 in parallel with M2, and then we have a RSS here. And here we have V in CM, that is V in CM is going to go to the gate of both M1 and M2. Now what do you mean by, you know that transistors are in parallel, resistances are in parallel are quite common, but what do you mean by transistors are in parallel? So let me just show that to you here. Here we have one transistor like this. This is drain, source, and this is the gate. And here we have another transistor. The source, gate, and this is the drain. And this is going to be GM1, VGS1, and this is GM2, VGS2. This is 1 by GM1, and this is 1 by GM2. So if I short this, so drain and drain are shorted, gate and gate are shorted, source and source are shorted. So what does this mean? If I want one drain here and one source here, yes, I can see that path, thank you. But now focus on this thing. So here, what you can see here is that in the top circuit, two current sources are in parallel. Two current sources are in parallel. So two current sources are in parallel means this will be GM1 VGS1 plus GM2 VGS2, and this will be your gate, and this is 1 by GM1 parallel to 1 by GM2. 1 by GM1 parallel to 1 by GM2. Now you can see that the VGS of both the transistors are same. This is drain, this is source. Why VGS is same? Because from this circuit you can see that this is gate, this is the gate, and source are connected to ground, and between gate and source we are having V in CM itself. We are having V in CM itself, and that is the reason why this can be written in this way: GM1 plus GM2 into a common VGS, where VGS is equal to VGS1 plus is equal to, not plus, equal to VGS. So now if we look at this M1 parallel to M2, what we have to do is only insert this here. So that gives me a AC model now, which is somewhat like this. I have a current source, I have a resistance, and here I am giving my V in CM. So this is drain, gate, source. This is 1 by GM1 parallel to 1 by GM2. This is GM1 plus GM2 into a VGS, and here at the drain and between VDD we have RD by 2, and let's say this is our V0. So this common point we will call it as some V0, and here at the source we have RSS, whose source we now know. Now very simple, once we have this model, we can simply write V0 is equal to minus GM1 plus GM2 into a VGS, that is the current, into RD by 2, and V in Cm is equal to the voltage drops across these two transistors, which is going to be simply GM1 plus GM2 into VGS into 1 by GM1 parallel to 1 by GM2 plus RSS. So if we take V01 upon V0Cm, that is going to be RD by 2 upon 1 by GM1 parallel to 1 by GM2 plus RSS, and if GM1 is equal to GM2, if GM1 is equal to GM2, what we will get here is something like this. So this V0 by V in Cm is called as ACM, that is the common mode gain, that is RD by 2 upon 1 by GM1 plus RSS. So ACM would be RD upon 1 by GM1 plus 2 times of RSS, or you can just leave it here like this. It doesn't matter. So what it means is that, now if you carefully observe this, somehow if we are able to make an ideal current source, this RSS will tend to infinity. If we are able to make an ideal current source, this RSS will tend to infinity. And if there is an infinity term in the denominator, then this value will become 0. This value will become what? ACM will become 0. That is exactly what we want. But this is never possible completely. And that is why we are now forced to find out what is the content of ACM as compared to AD. What is the ratio of AC as compared to AD? And that can be done in terms of a ratio called as CMRR. So CMRR would be AD by ACM, and AD was, I will write here, minus GM times of RD Okay, and here let us say that gm1 equal to gm2 equal to gm. So here I will just write simply gm. So here what we are going to get is rd by 2 upon 1 by 2 times of gm plus rss. Now rd cancels off, this 2 will go at the top, so I'll get minus 2 gm upon this is 1 into, we can write 1 by 2 times of gm plus rss, and if we multiply this thing inside, we will get 1 plus 2 gm into rss. If I'm not wrong, please check that calculation and let me know. So you can see that if RSS tends to infinity, CMRR will also be infinite. But if we are not able to make good MOSFETs or good current sources, this CMRR will slightly reduce. So our effort should always be that we should have very high CMRRs. That means my differential gain should be always greater than the common mode gain, and that will ensure that the noise is suppressed and we get very high gains and we get very high gains. So I am just going back so that you can copy this. First you will copy this circuit, show ISS as M3, then say that M3, if it is acting like a current source, it will always operate in saturation region. But in saturation region, if M3 is very small in size, then since the device is scaled down, the channel length modulation may come into the picture and cause a slope in the output characteristics. A slope in the output characteristics means a very high resistance value, not infinite value, but very high resistance value. So I replace that M3 by RSS in the next circuit, and I mention there very well the resistance is very high, but it is not infinite. But it is not infinite. Now, since V in 1 is the same as V in 2, we can expect that ID1 will also be same as ID2, because when you are giving same inputs at the gate, common mode, then ID1 will also be equal to ID2, and as a result, V01 will also be equal to V02, because formula wise V01 is nothing but VDD minus ID1 RD, and V02 is VDD minus ID2 RD. So if ID1 and ID2 are same, and if the resistances are also the same, V01 will be the same as V02. Same as V01 is equal to V02 means what? They are at the same potential. They are at the same potential, and if the 2 points are at the same potential, then we can simply show them connected by a wire. We can simply show them connected by a wire, which I did here. And when I did that, so this is not a wire, there is no wire like this, but they are at the same potential. So we can imagine that they are like this, and this gives rise to RD becoming in parallel with this RD, which gives me this circuit, that is RD1, RD parallel to RD, RD by 2, and the M1 and M2, that is this drain of M1 is connected to drain of M2, source of M1 is connected to source of M2, gate of M1 is connected to gate of M2. So the way to show that is like this. The way to show that is this way. But when we did that, this is M1, this is M2. When we shorted the gate, drain, and source, we saw that the current sources are coming in parallel. So current sources in parallel will add up and give me a higher current source having this value GM1 plus GM2 into VGS, and two resistances in parallel obviously will give me a parallel resistance, that is 1 by GM1 and 1 by GM2. So taking that concept further, now I am inserting this at this place. So actually this model represents M1 parallel with M2, and once we do that, we get V0 as minus of current flowing through RD by 2 is GM1 plus GM2 VGS, and so I multiply that. V in Cm is the voltage drop across this resistance and this one, and the current flowing through these two resistances is nothing but, I will say I, and I is equal to this value. So whatever that value is, that cancels out. So this cancels out with this, VGS cancels out with this, and what remains is these two terms which I wrote here. And then I made a special case here, that is, what if GM1 is equal to GM2? So I get ACM. Similar to something that what we did in the differential formula calculation. So we want to now find out how good this differential amplifier is. So we say that CMRR should ideally be infinite, that is ACM should be 0, but that is never going to happen ideally because RSS will never be infinity. And this is the technological glitch that now if you want to make, let us say, an ADC, an A to D converter, which will require a differential amplifier in it, how small can you make that is the challenge. And if you try to make the differential amplifier very, very small in size, then your CMRR is going to get affected. So in the exam, they may ask you in the Viva that if I try to reduce the size of the MOSFETs in a differential amplifier, will my CMRR increase or decrease? So the answer will be the CMRR will decrease. The reason is because of channel length modulation, which will give rise to RSS, and RSS is going to be the main culprit. So if RSS is finite, CMRR is also finite. And what is CMRR? CMRR stands for common mode rejection ratio. Common mode rejection ratio. So any doubts in this? Unmute and ask. Yes, Ashlesha Mahajan, have you understood these concepts? Shubham, Shubham Dalvi, Shubham Vairkar, have you understood this? Yes, Shubham, you had raised your hand. Do you have any doubt?
No, sir.
Okay, so I am done for the day from my side.